This is the first of several recordings for Chapter 7. This is the respiratory system and its regulation. A little bit of introduction to this chapter. Primarily what we're going to be talking about with the respiratory system is gas transport. And when we talk about gas, we're primarily talking about oxygen and carbon dioxide. So the cardiovascular and respiratory systems work together to bring air into the lungs. From that air, we take out oxygen and we deliver oxygen from the lungs out into our tissues. And our tissues are also picking up, our tissues are producing carbon dioxide, which gets transported to the lungs, and from the lungs we can get rid of it. So together the cardiovascular and respiratory systems are bringing oxygen into the body and removing CO2 from the body. We're going to talk about these processes in 4 steps. The first one is pulmonary ventilation. Okay, pulmonary ventilation is basically breathing, so it's taking air in and out of the lungs. And remember that when we say air, we don't mean oxygen, okay, because the air in the atmosphere contains oxygen, it contains CO2, it contains helium, it contains nitrogen, so air does not mean oxygen, so be careful with that. Once the air gets into the lungs, we have something called pulmonary diffusion, and this is just gas movement between the lungs and the blood. So oxygen will come into the lungs and then enter the blood. CO2 will be already in the blood, and from there it will diffuse into the lungs so we can get rid of it. So gas exchange between the lungs and the blood is called pulmonary diffusion. Once the gases are in the blood, they need to be transported. So oxygen is transported away from the lungs out to the body, and CO2 is being picked up by the tissues and being transferred or transported through the blood up to the lungs. Capillary diffusion is the exchange of gases between the blood and the tissues. And when I say tissues, I mean cells. Okay, we primarily, in this class, we're talking about muscle cells, but other cells in the body are receiving gases and producing gases. And so the exchange of oxygen from the blood into the tissues is called capillary diffusion, or the exchange of CO2 from the tissues into the blood is also called capillary diffusion. So we'll talk about these one at a time. A little bit of background on lungs. You should have already learned this when you took human physiology and anatomy. But basically, our air comes in through your nasal cavity and through your mouth. Okay. Once the air gets into your nasal cavity, into your mouth, it goes into your pharynx. From the pharynx, it enters the larynx, and from the larynx, it enters the trachea. Okay. After the larynx, the air can either go into the trachea or the esophagus. Hopefully it goes to the trachea and not the esophagus. From the trachea, the air travels down and branches out into the lungs, and it enters the bronchial tree. So smaller and smaller air passageways until finally the air ends up in what are called alveoli, which is the plural, or alveolus, which is the single. So there's about 300 million alveoli in the human lungs, so they're very, very tiny, and they're just millions of air sacs, and that's where our air ends up. And then each of these alveoli is surrounded by a very dense network of capillaries, and that's where the exchange can occur. Okay, that's where pulmonary diffusion occurs. It's between the alveoli and the capillaries surrounding the alveoli. A little bit more anatomy just to give you some background. The lungs are suspended in your chest by pleural sacs. So the lungs themselves are not actually attached to the chest wall. The lungs are surrounded by two different pleura, the parietal pleura and the visceral pleura. Okay. The parietal pleura is actually connected to the thoracic wall. So the parietal pleura is connected to the chest cavity. The visceral pleura is attached directly to the lungs. So the visceral pleura is the inner membrane that is attached to the lungs. In between the two pleura is what we call the pleural cavity. So that's that white space here in between. And the pleural cavity is a space between the parietal and the visceral pleura. It contains what we call pleural fluid, which is a slimy fluid that helps reduce friction during breathing. So when the lungs are expanding and contracting, the pleural fluid helps prevent the pleura from rubbing against each other. Also in the pleural cavity we have a suction that holds the lungs tight against the thoracic cavity. So again, it's important to know that the lungs themselves are not attached to the walls of the thoracic cavity, but they are held to the walls with this suction which is within the pleural cavity. Okay? So the visceral pleura is attached to the thoracic cavity. Okay? The parietal pleura is attached to the lungs. In between we have this pleural cavity with a pleural fluid and also a suction that keeps the lungs essentially attached to the thoracic cavity, although they're not actually physically in contact. So one way to think of it is if you take two pieces of glass and you put water in between them, the two pieces of glass stick together. Even though the two pieces of glass aren't touching each other, there is a suction that forms between the two pieces of glass within the water that prevents you from pulling the glass apart. So the glass is connected to the other piece of glass without physically contacting it. And that's what's going on with the lungs, is that the lungs are basically attached to the thoracic cavity. They're going to do whatever the thoracic cavity does, not because they're physically in contact, but because of this suction within the pleural cavity causing this connection. All right, some basic definitions. Pulmonary volumes. Breathing frequency is the number of breaths that you take per minute. Okay, in a clinical setting, they call this respiratory rate, abbreviated RR. In physiology, for some reason, we don't usually use the term respiration rate. We use the term breathing frequency. So it's the number of breaths per minute. Tidal volume, so the V is for volume, the small t is for tidal. Tidal volume is the volume of air that's moved either in or out of the lungs each time you take a breath. And then the pulmonary ventilation, capital V, small e, is the volume of air that's moved per minute. Okay, so this is breathing frequency, which is breaths per minute, times tidal volume, which is milliliters of air per breath. Okay, and the breaths will cancel, and you end up with milliliters per minute. Okay, but pulmonary ventilation is expressed in liters per minute, not mLs per minute. So we would need to convert our milliliters per minute to liters per minute. Okay, let me show you an example of that. Okay, so if you had some typical values would be 12 breaths per minute. That's a normal breathing frequency at rest. And if you multiply that by a normal tidal volume, which is about 500 milliliters that we take in with each breath, Okay, you do the math and you end up with 6,000 milliliters per minute. Okay, but we want to convert that into liters. Okay, and 1 liter is 1,000 milliliters. Okay, and 6,000 divided by 1,000 is 6.0. Okay, so a normal resting ventilation rate is about 6 liters per minute. Okay, so it's frequency times tidal volume converted into liters, and we have total breathing frequency. Hopefully you see that these numbers are similar to the numbers we talk about in the cardiovascular system. When we talk about frequency, we talk about heart rate in terms of the heart is the number of times it beats per minute. The volume is the amount of blood that comes out of the heart with each beat, and then the total cardiac output is the total amount of blood that comes out of the heart per minute. So similar numbers, but instead of talking about blood, we're talking about air. Okay, a couple basic concepts, and these should sound familiar, is we're going to talk about how and why air moves the way it moves into and out of the lungs. As with blood flow, which we talked about in the cardiovascular chapter, air flows due to a pressure gradient. Okay, and air is going to flow down a pressure gradient. So it's always going to flow from an area of high pressure to an area of low pressure. Okay, and that high pressure is P1, the low pressure is P2, and the gradient is P1 minus P2. Okay, and as with blood, the bigger the gradient, the faster the air is going to flow. Alright, so the two pressures that we're talking about are the pressure in the atmosphere versus the pressure inside the lungs. So we call that intrapulmonary pressure. We can also call that alveolar pressure. It's basically the pressure in those air sacs. And so air is either going to move from the atmosphere into the lungs, that's inspiration, or it's going to move from the lungs out into the atmosphere, that's expiration. And the factor that determines which direction air moves is basically where is the pressure higher, where is the air pressure higher, in the atmosphere or in the lungs. If the pressure is greater in the atmosphere, okay, which direction is the air going to flow? Okay, it's going to flow from high to low. So it's going to flow from the atmosphere into the lungs. Okay, because if atmospheric pressure is greater than intrapulmonary pressure, okay, then it's going to flow from where it's highest to where it's lower. Okay. On the other hand, if the lung pressure in the lungs is greater than the pressure in the atmosphere, we're going to have the reverse. We're going to have blood flowing from the lungs out into the atmosphere. Okay? Because again, it's going to flow from where it's higher to where it's lower. Okay? So when you inhale, the reason air is coming in is because the pressure in the atmosphere is greater than the pressure in the lungs. And when you exhale, the reason you exhale and the reason air moves out of your lungs is because the pressure in the lungs is greater than the pressure in the atmosphere. Okay? So there must be some way to manipulate these pressures, to change this pressure gradient. Now, you have no control over atmospheric pressure. Okay, that's the pressure in the atmosphere. But what you do have control over is intrapulmonary pressure. Okay? So the human body has ability to manipulate intrapulmonary pressure, And by changing intrapulmonary pressure, you set up a gradient that's either going to cause air to flow in or out. Alright, so before we talk about air movement, so we've reviewed this concept that we've talked about again and again, and it's still going to come up some more this semester. We need to talk about Boyle's law. So Boyle's law is very simple. It says that the volume of a container of gas is inversely related to the pressure of the gas in that container, as long as the temperature is constant. Okay, and let me show you really simply what that means. So if you increase the volume of a container of gas, because the relationship is inverse, the pressure of that gas is going to go down. And vice versa, if the container holding the gas gets smaller, then the pressure of the gas in that container is going to go up. Okay, let me just show you what that looks like. Alright, so you have a container of gas. And let's say this container is 1 liter, and there's some gases in that container. Basically, the pressure of the gases in the container are related to the number of gas molecule collisions. Okay, so when these gas molecules collide, they cause pressure. Okay? They generate pressure. So let's say that in a 1 liter container, you've got gas, and the pressure exerted by those gases is 200 millimeters of mercury. Okay? But let's say we take that same gas, and we double the container. Okay, so we change the container. We take the same amount of gas, we put it into a 2 liter container, so we've made the container twice as big, and because the gases have more space between each other, they're going to collide less frequently. Okay, so by increasing the volume, we end up with a decrease in pressure. So the pressure of the gas in this container will only be 100 millimeters of mercury. Okay, so we increased volume, which decreased pressure. On the other hand, if we take those same gases and put them in a container half the size, so say we put it in a 1/2 liter container, got the same amount of gas, but because the container is smaller, you're going to get more collisions. So you're going to have more pressure. Okay, and so we're going to have, since the container is half the size, we're going to have twice as much pressure. Okay? So when we decrease volume, we increase pressure. So, the pressure of gas in a container is inversely related to the size of the container. So if you increase the volume of the container, you're going to decrease pressure because you're going to get less collisions. If you decrease the size of the container, you're going to increase pressure because you're going to get more collisions. Okay? So very simple concept. Now remember that our lungs are containers that hold gas. Okay? So if we want to change intrapulmonary pressure, we can do so by changing the volume of our lungs. Okay? And when you inhale and exhale, your lung volume is changing. Your lungs are expanding, your lungs are contracting. Okay? When they expand, the volume of the lungs gets bigger, and therefore the pressure of the gases in your lungs is going to get smaller. Okay, when your lungs contract and get smaller, the volume is smaller. The volume holding that gas is smaller, and therefore the pressure of the gas within the lungs is going to go up. And that's basically what we do when we breathe, is we manipulate the volume of the lungs in order to manipulate intrapulmonary pressure in order to generate a pressure gradient that's going to move gas in the direction we want it to and need it to move. All right, respiratory cycle. There are two phases of a respiratory cycle. There's inspiration and expiration. So inspiration is when you inhale and you bring air from the atmosphere into the lungs. And expiration is when you exhale and you take air from the lungs and you put it out into the atmosphere. And we're going to talk about these on the next recording. But for now, what I want you to understand is that at rest, resting breathing, inspiration is active. Okay, remember the terms active and passive when we talked about them in terms of blood moving through the heart. So if inspiration is active at rest, that means that some type of work is being done. ATP is being used in order to generate the pressure gradient that's going to move air into the lungs. During exercise, inspiration becomes even more active. Okay, which means that during exercise we have to do more work and we have to use more ATP in order to bring greater amounts of air in, which we need during exercise. And therefore some additional muscles become involved. And we're going to cover this in detail in the next recording, but I just want to set this up for now. Expiration at rest is passive. Okay? And what that means is in order to get air out of the lungs, we don't have to do any work. We don't have to use any ATP. So expiration at rest is passive because air will come out due to a natural pressure gradient that exists. So we don't have to do any work to exhale. However, during exercise, particularly as the exercise becomes heavier, expiration becomes active. So we need some help to getting air out because during exercise we need to exhale more quickly, and so we can't rely on the passive forces. And so during a heavy exercise, expiration does become active, and you will see that on a future slide. Okay?